Good afternoon, everybody, and our invited scholars, and then every audience in here. Welcome to the international, not international, the BrainLink Accept Day talk concert. Today's event is sponsored by the Korean Federation of Science and Technology Societies, and the Korean Society of Intelligent Transport System has been preparing this event and to invite the scholars from overseas and domestic. So this is a moderator. My name is Jaehyun So. I'm an associate professor of Aju University. So I'll be moderating for today's event, and I'm so honored to have you all here. And then probably it's a nice, the first time meeting with most of you here. So I'm so happy to have you and very honored to have you here. So we are here for the talk concert titled "The Future of Automated Mobility Through 5G Plus Vehicle Connectivity and the Infrastructure Acquisition and Innovative Application Strategies." So I believe this is one of the excited subject among the talk series, and I also very look forward to hearing many good presentations and your insightful discussions. So before we begin, I would like to introduce to our several distinguished guests, keynote speakers. So first of all, I'm a organizer from domestic side, and we have another organizer from overseas. So the name is Professor Brian Park from University of Virginia. You probably just give him a big applause. And then second, Professor Raul Mangaram, and please give him a big applause. Yeah. And third, Dr. Mang Lu. Yeah. And Professor Xiaopeng Li. And then Professor Junseok Oh. And Professor Andres Malikopoulos. Yep. And Professor Simeon Calvert. And Professor Randall Rubik. Yep. And here, this is our kind of a list of our invited guests, invited speakers, but we still have a honored and great scholars here from domestic. So I actually want you. So before we push the main event, we have a video, right? So this is the time for that, right? Yeah. Okay. So.
Amidst the world's rapidly accelerating changes and competition, what kind of future are you preparing for? We are chartering a path to the future through science and technology exchanges, bolstered by international cooperation. In this era, where scientific and technological competitiveness is directly linked to a nation's diplomacy and security, the power to overcome such challenges lies in international cooperation that fosters synergy through collective efforts, and from talents who will shape the forthcoming era. The scholars of the world are gathering in Korea. A platform that facilitates exchanges between Korean and international scholars, as well as between seasoned and emerging researchers, is taking shape. BrainLink X Lab Day, organized by the Korean Federation of Science and Technology Societies, aims to be a global hub of talent. By consistently enhancing and expanding the global talent network, we're laying the groundwork for a brighter future. By inviting global scholars, X Lab Day provides an opportunity for young Korean researchers to glean insights from the vast knowledge and experience of both Korean and international scholars, as well as to engage in collaborative research. BrainLink X Lab Day establishes a global science and technology network among overseas scholars and Korean researchers. In 2024, BrainLink X Lab Day will be joined by globally renowned scholars, including Professor Luke Pyeong-se Lee of Harvard Medical School, Professor Andrew Goodwin of University of Oxford, Emeritus Professor Teruo Okano of Tokyo Women's Medical University, Jeffrey Newmark of NASA Goddard Space Flight Center Research Astrophysics, and Professor Dan I. Anderson of Uppsala University. The discussions will span 12 national strategic technology fields, pivotal to Korea's advancement, including the three game changers: quantum mechanics, nuclear technology, and AI. The event will see the participation of 40 Korean and international scientists and engineers. With two organizers leading each technical segment, the gathering will foster in-depth academic exchanges, encompassing the sharing of recent trends and information in core technology fields, in-depth discussions on research findings, and the sharing of ideas. And talk concerts will be held in collaboration with all BrainLink XLab Day sessions. The focus of XLab Day is connectivity and sustainability. Following the event, communities and clubs will be established based on each XLab Day session to ensure ongoing dialogue among attendees and promote collaborative research. COAST supports the reinforcement and expansion of the networks established through XLab Day. COAST, the organizer of XLab Day, stands as a beacon for Korea's science and technology society. Established in 1966, its mission has been to safeguard and amplify the rights and interests of scientists and engineers. Our endeavors extend to enhancing the public's grasp of science and technology and furthering its development through comprehensive policy research, planning, surveys, and consultations. As Korea's largest science and technology network with over 600 affiliated organizations, we are committed to promoting domestic and international cooperation and exchange. In the transformative era of the Fourth Industrial Revolution, where science and technology spearhead groundbreaking challenges, COAST remains dedicated to its role as a facilitator of scientific and technological innovations.
안녕하십니까. 한국과학기술단체 총연합회 회장 이태식입니다. 과총은 사회 참여 확대와 권익 신장을 도모하기 위해서 1966년 설립한 공익법인으로서 과학기술단체 육성 지원과 다양한 정책 연구, 기획, 조사, 자문을 통해 과학기술 발전에 기여하고 있습니다. 저는 2023년 과총회장으로 취임하여 새로운 도약을 위한 비전, 프라이드 코스를 선언하였으며 이를 실현하기 위한 운영 목표와 추진 전략을 중심으로 빛나는 100년을 향해 모든 역량을 집중해 나가고 있습니다. 더 나아가 우리나라가 미래 핵심 기술 분야를 선도하는 기술 주권 국가로 자리매김하도록 국가적인 원팀 플레이를 이루는 데 있어 강력한 조력자가 되겠습니다. 대단히 감사합니다.
BrainLink XLab Day aims to broaden both domestic and international talent networks and become a global hub of talent. By making XLab Day into an event that scientists and engineers worldwide eagerly join, we intend to elevate Korea's global standing and bolster national competitiveness. Global Talent Hub, BrainLink XLab Day.
So, yeah, was great. So thanks, COPS, for supporting everything about this conference. And then COPS is the organizer, actually the main sponsor and organizer of this conference and workshop. So thanks for that. So, as far as I know, what this workshop is somewhat different with just a normal conference or workshop, because presentations and research things, that's great, but just making opportunity to be collaborated and making connections, that's another important goal of this workshop. So I hope you make a great relationship with others and then try to make it and during break time or dinner. So, and this is not actually main event, and main event is starting from tomorrow until Friday. So you still have many chances to make a collaboration. So I hope that works very well. Okay, so so this is the time to begin the show. So we're supposed to have 4 presentations, 10 minutes each, and then we're gonna start the first session, the presentation session. So we have 4 presenters here. So we're actually starting from our overseas organizer, Professor Brian Park, University of Virginia. So are you ready? Yeah. Okay, so yeah, please welcome him with a big applause. So he's gonna. Just relax.
Thank you. I guess we have not done any dry runs. My name is Brian Park. I work with Jason So to organize this event, and thanks everyone for coming, especially guests. Given 10 minutes, I'm going to talk about my research, just a little bit of highlights. My research focus has been how to actually improve efficiency when fully connected and automated vehicles coexist with the human-driven vehicles, and what can we do about it? And want to show some challenges and opportunities. I'm going to skip this one, but when I show the photo of a beautiful Charlottesville downtown university campus and Monticello area, that's I wanted to show that. If you look at the history about self-driving cars, amazingly, this was started back in 1925. We're almost 100 years. And we seem to getting closer and closer, but there's a big gap in opportunities, reliability and other things. Might have seen a lot of videos, something like this. This is US DOT, Department of Transportation, demoing cooperative adaptive cruise control. This obviously fully automated vehicles, fully connected to each other. And one of the things they have to do is understanding leader vehicles, sort of a motion of acceleration, deceleration, and they have to get them by communications. Using sensors is a kind of delays and other things. Doing that is also a challenge, something I will actually talk about it later. When you look at this fully connected and automated vehicles, this will actually make a huge change. If cars can follow about 0.6 seconds apart each other, assuming humans are doing 1.8, 3 times more vehicles can get through, which is a breakthrough for existing facilities. This will be huge benefit. But this requires obviously 100% fully connected and automated vehicles. This can be realized when we get 100% or when we try dedicated lanes for doing these, which is also a challenge. Think about when high occupancy vehicle or high occupancy toll lanes came out, so empty syndrome, and it's only good for those who reach and things like that. So what happens if fully connected and automated vehicles are interacting with the human-driven vehicle, sort of mixed traffic the way I defined? CAV has to fall back to adaptive cruise control, which a lot of vehicles currently have. And is ACC good? Some people like it, some people hate it, depending on how they use, but it's not as good as a cooperative adaptive cruise control. We call it string stable conditions. That means a very smooth traffic. ACC to achieve that needs over 2 seconds of time headway. If it's not, then it's a lot of oscillation, the changing acceleration, too much acceleration. Oftentimes, ACCs use more energy fuels compared to CACC, so that's a challenge. So my research is, look at the bottom side. If CAV follows a human-driven vehicle, But second preceding vehicle has a connectivity. It doesn't have to be connected and automated vehicles. If they can actually share their information about intended acceleration and deceleration, can we actually use that information to have the connected automated vehicle doing better than simple ACC? That's sort of my research topic. So the idea is we want to design a control algorithm such that the ego vehicle, vehicle 0, can actually take advantage of not the first vehicle, but second preceding vehicles intended acceleration, deceleration. So the idea is when we actually have that, we have to assume behavior of immediate preceding vehicle. We have sensors of understanding and all that. The way we design the algorithm is this number one, unconnected human-driven vehicle will be somewhat reasonable. So it could actually hit the leader vehicle by super acceleration, or it could actually have a deceleration, try to create a rear-end collisions. We assume they're not doing that. Most of the time, they don't do that. So 97.5% of the time, they don't do that is our assumption, and we developed the algorithm that basically using second preceding vehicle and very simple prediction of the number one vehicle, and the ego vehicle's control is determined by smooth traffic maximization algorithm. So this is a sort of a comparison. When we use a simple ACC with about 1.5 second time headway, ACC cannot have a smooth car following. We call it overshooting speed. So its speed is higher than preceding vehicle speed, or if speed is lower than preceding speed when it decelerates. And that's kind of showing a lot of points here. When we use our algorithm, as you can see, the ego vehicle is a red color. So it never goes above preceding vehicle speed when it goes up speed. When it slow down, it never goes below. So it's a very smooth following, and it can give the advantage of safe distance and also saving fuel consumption and so forth. So we wanted to do this in real field tests. But a lot of times the people don't trust when we do simulation-based approach. So we worked with the KAIST on these efforts and created a vehicle. So the way we have it done was they have two automated vehicles, and they can actually replay trajectory data. So real trajectory data we have, and then number, first vehicle is basically replay same thing, so that we can actually have an ego vehicle doing human-driven ACC and our algorithm, CACCU. And we don't really need to have a second preceding vehicle because all it does is sending intended acceleration. It actually coming out from number two vehicle. And as you can see here, it gets a fairly large benefit. And you can see compared to ACC, not human-driven. Human-driven could be really worse. It's slightly better than ACC, but most of the time it varies. But ACC, given the algorithm, they have the same way of doing it. We did 3 different test algorithms, and our algorithm can save about 10.8% acceleration changes. This means smooth, and also saving fuel consumptions, and spacing errors are reduced, improving safety, and also fuel consumption savings. If this is CACCU, what we developed, will actually make an impact on general traffic condition is what we are looking at. And if we're looking at this one as a different combination of control options. So without having connectivity, cars can do adaptive cruise control. With the connectivity, cars can do cooperative adaptive cruise control, which is a B. C is even without having high number of market penetration rate, our ego vehicle can actually see the second preceding vehicle information and try to do better control, so including the CACCU. And with these, a lot of simulation was done. I'm just showing the essence of the algorithm. So we're comparing AV functionality as ACC and CACC algorithm ACC, and the CAV means including CACCU algorithms. And then these are simulation, but based on different market penetration rates. Starting from 1% CAV and 1% connected vehicles. And going to about 40 to 40% means only 20% of cars are human-driven vehicles. All these variations. Most of the promising results we are seeing is even about 10% of connected vehicle or connected and automated vehicles The line that we are showing here is maximum unsafe spacing errors depending on market penetration rate. And even about 10% case, we are seeing benefits compared to ACC condition or CACC alone. Note that CACC to work, it has to be fully connected vehicle, connected automated vehicle at a sequence. And our algorithm can actually do even without having same pair of vehicles available. So that's a huge difference we are getting. Same thing with the fuel savings, and that's advantages. So this is how we can actually do. Even we include a strategic lane change, it gets a lot better, and that's not I'm going to talk about, but that's the sort of ideas. Before I conclude, one of the challenging things on this research is because of privacy concerns, cars are not sharing their license plate, not even their color or vehicle or vehicle types. Their messages are encrypted. So with the encrypted messages, we don't know which lane they are on based on current GPS errors. How to identify, properly connect the vehicle, and start engaging in communication of control is one of the big challenges. Thank you very much.
Yeah, thanks, Professor Park. I regret not to have more comments this time, but I look forward to have more comments from what discussion session. Okay, so let's go on to the next presentation. And the second speaker we have Professor Rahul Mangaram from University of Pennsylvania, and you're supposed to be talking about the mad games, right? So okay, so please give him a big applause. Yeah.
All right, thank you for having me here. I'm Rahul Mangaram from the University of Pennsylvania. Just by way of introduction, I wear a couple of different hats. So one hat I wear is I serve as the Penn Director for the Department of Transportation, National University Transportation Center. And this is a collaboration with Carnegie Mellon, where I used to be before. And so this is the $20 million center, and we've been running these kind of centers for over a decade. The second hat I wear is with industry relations. We work with over 70 plus industry members as part of the Autoware Foundation. This is a nonprofit consortium that develops the world's leading autonomous vehicle stack, software stack, and that allows us to have a lot of collaborations with industry. And I also serve as the director of the Autoware Center of Excellence, which has over 28 university members that actually use Autoware on their research vehicles. And finally, I started the F110th Foundation, which has autonomous racing cars that are 1/10 the scale. And that's in over 89 universities. And actually, just last week, we had over 37 teams in Korea, in Jeju Island, compete in that. So today, I'm going to talk about something very exciting and very quickly, hopefully. And that's on AI agents in the physical world. And that's how I see the vehicles actually today as. And so this is on, so if you, in the past decade, we worked on a lot of research projects for looking at autonomous vehicles and the traffic and so on. But if you see that car that's trying to merge in over there, the yellow truck is not giving it. So for you and me, we can eventually get in and we know how to nudge and make do. But for autonomous vehicles, this is a non-cooperative scenario, and they really struggle with these competing objectives. They don't understand intention. And I don't mean just human intention, they just don't understand intention. And so we were like, okay, well, for you and me, we want to get home, and we want to get home safely. So safety is maximized in the first scenario, but performance, if I get home like 5 minutes later, no big deal. So we didn't have this tension in the problem. So we said, well, we need tension as control engineers. And so we looked at autonomous racing. Here you get penalized for being overly conservative if you're too slow, or you get penalized if you're being overly aggressive. In fact, if you're half a second too slow in your lap time, you're out of the top 10. Yeah, that's your career decision over there. But it's not all about being too fast. Only 40% of the F1 winners had the fastest lap times. It's more about balancing safety and restraint and deciding that on the context and in real time. And here we are also operating with full physics, like that, the full dynamics of the vehicles, because if you are not operating at the nonlinear knee of your vehicle's performance and the tire limits, your competition is, and they're going to outcompete you. So fast reactions, high accelerations, very high speeds. And so we see, well, obviously crashing is expensive and dangerous. And the sensors that we have, LiDARs, cameras, radars, they'll tell you the pose and the short-term prediction of the other vehicle's trajectory, but they don't tell you what we really want to know in connected vehicles. What is the driver's intention? What is their policy? And the policy means what is the trajectory they're going to generate for every turn in the future as we see them. And the sensors don't tell us that, and that's the goal of our first part of our research. Strategies in racing are also secret. We can't just use supervised learning. Every race is different. The competitors are different. And so that's our goal is that by focusing on racing, we can bring safety through agility by having superhuman drivers. And so the first was a research topic that I'll talk about much more tomorrow. I'm just going to give you a very quick overview is how do we understand intent? How do we generate the most competitive agents that can balance safety and performance? And so this is part of the work we had in ICML, and that is really looking at how we can generate really competent agents offline, and then online, we actually make them compete, and we identify other agents to say, oh, well, if I have 20 agents as part of my agents that I've generated offline, maybe you are a different weight of that agent, and I can figure out what your policy is. Once I can figure out your policy, I can drive very aggressively next to you because I know what your trajectories are going to be, but I'm also going to be very safe. So we can actually achieve that, and what we show is that in racing, we can actually maximize safety while achieving the highest win rate. So here, this is saying that, well, we are not trading off safety and performance. We are using our power of adaptivity by online learning to be able to achieve that. And whatever we do in theory, we also do in practice. These are our scaled vehicles, and they show that system actually working in real time. And the other agent doesn't know anything about the strategy of the other vehicle, the lead vehicle, and they can outcompete them. So we'll go more on this. We put this in a game theoretic context. You know, game theory, as I was discussing with Andreas on the way here, it's very hard to make it practical. But here we actually look at it as, well, if I'm operating in this sort of game with other agents, even when we are driving, we don't know if the other agents are competitive, adversarial, cooperative, collaborative. There's a mix of those agents. So we take this problem, and I'll discuss this much more tomorrow, and we show how we can solve this problem online. And so this is using reinforcement learning, but adapting online, and you become very powerful in how your agents can actually now work against other agents. We also have different theoretical approaches for adaptivity, and this is looking at, say, these control barrier functions, which are mathematical ways to express safety in these systems. And this allows us to now, but they are too static. So here we want to adapt how conservative we want to be and how less conservative we want to be as we go through the systems. And so we built an approach where we can actually learn how to manage and manipulate our conservativeness through this, and therefore we can see how this scales. This scales with the number of agents. This generalizes to agents with different driving behavior, and this also works in unseen driving scenarios like that, right? So a lot of our work uses like learned control barrier functions, conformal prediction, and physics-informed machine learning. And that's just the first part. Our lab is a very fun lab. We have a lot of representation from different countries. And the other themes are on how can we optimize for autonomy. So here we want to design the fastest vehicle, but the tracks keep changing. And so here you can say, okay, well, I want to optimize the mechanical properties, the control properties, the planning, and the decision making. And say if the lap time is 25, I can manually try to tweak this. The lap time becomes 20. The lap time goes all the way to 15. Here the vehicle is now drifting, and I've reached the maximal sort of potential of this vehicle now. But the question is, how can we do this automatically? So this was work from ICRA called Tuner Car that does super optimization across multiple domains of optimization, mechanical, control, decision making. And everything what we can generate now is a vehicle that can drive the fastest, no matter what track you give it and what vehicle design you give it, it will optimize the autonomous vehicle stack for that. The third sort of theme is, well, we don't want to design a new vehicle from scratch. This goes all the way to manufacturing. We want to use previous designs to generate new designs for new requirements. So this is kind of like the Iron Man theme. We want to do autocomplete of designs. So we built an entire pipeline of how we can take previous designs, put them in a knowledge graph, mine them, and then generate new designs for new requirements. And we did that for drones, and we could generate the human-made drones. We could generate now computer-aided drones, and they all physically, they are very weird and funny designs over there, but they are all dynamically viable and feasible drones. And so for different benchmarks of how fast they can go, how far they can go, we can generate different designs. And I'll talk about, these are now generated designs going across the stack, and so that they can maximize their benchmark capability. And so generally, we focus on a lot of these themes. I'll speak for 2 more minutes about what we do in education. So we have this autonomous racing competitions. But the whole idea is if you want to design an autonomous system, you need to know all these different disciplines. And how do you now put them together? So we've designed this 1/10 scale autonomous racing vehicle. And with that, we can actually show that the students can actually use these, and they can actually drive them, race them, crash them, but learn the full stack, learn perception, planning, control. They can use our simulators along with this. Everything is open sourced, and we helped the community build, code, and race. We've developed open source courses that is taught in dozens of universities, and the good part is there are no exams, there are only races, actually. And they compete, and they basically grow in sophistication of this, right? So we have competitions all over the world. In fact, we've had 2 competitions just this year in Jeju, and one was just last week, as I mentioned. And and both were very successful, and this is an example of what a competition would look like. This is in Jeju, and these cars are racing against each other. It's not sped up. And this is just the final lap and how the cars are basically working with. And so this really brings together the robotics community, the transportation community, and many different communities. And this is in the robotics conferences. And this has over 89 universities that are part of this program, right? So we also have theoretical work on MAD games, or multi-agent dynamic games. No systems, just really looking at the math behind all of these approaches. And lastly, we'll also engage with a lot of industry with AutoWare. And so this brings together the software that runs in all of these vehicles, but we want to bring the R&D from academia into this open source stack over here. And essentially, our focus is on designing the future EV and AV vehicles when you come to a skateboard chassis and you have an API for autonomy. And we're designing the API modules for the autonomy on these. And so this is software-defined manufacturing, software-defined vehicles, software-defined testing, and software-defined sensing. We'll go into more details on that tomorrow. We have our garage labs where we design these vehicles from scratch, and we have them from small scale, mid scale, to full scale, all running the same software. I'll skip over all of this part. I'll talk about it next time, tomorrow. But I just wanted to highlight one thing over here is that we have the same vehicles being manufactured now in Ulsan. And we have over 30 university professors that are part of our community now. And we launched the AutoWare Center of Excellence in Korea. And so we have a lot of engagement, and so I welcome you all to come and collaborate with us because we have very open standards and open vehicle platforms. Thank you.
Thank you very much, Professor Mangaram, and for sharing a lot of interesting stories and then photos. So you talked about the game stories and the racing stories, so everything sounds very interesting. So I more look forward to having your main presentation during the main days. Okay, so let's go on the next. We have a third presenter, Dr. Meng Lu from ALX ITS, right? Yeah, so please give her a big applause. Yeah.
Yeah, I can just start. Hello, everyone. Thanks for the organizers giving us the opportunity to meet together. Thank you all for coming to discuss the topic I love. Also, I've been working for around 20 years in the past. Different from the other speakers, I've been working for industry, mainly for the R&D, I've been working for different companies. Also, when I was consulting, I also worked for universities. Also for authorities, different heads, different activities. So for today, I'm affiliated with myself. So what I present is my personal view. Still, I would like to give some words about IEEE that I'm actively involved. So IEEE is the largest technical professional organization. You may know we have a large amount of members, 470 plus thousand. And we have our standards. Thousands are under preparation, and also more than 1,000 plus have been published. We also have conferences, technical activities, education, and many others. So you are familiar with IEEE journals, our transactions, and magazines. So a quick break. So IEEE was traditionally really engineering, let's say industry-driven engineers. We know Thomas Edison, Edison Bell, Tesla. We also know that this merge of the two institutes and it's formed IEEE. Although currently IEEE may give people impression that it's an academic group, but actually originally not. And currently we're also trying to bring more industry, let's say, members to be actively involved, also to make research work also connected with application. Academia meet industry, we also have similar goals. And the society, I'm from Intelligent Transportation System Society, we call that ITS. I know this automated driving has been talked by different people from different domains. I can see some people from computer science, some people from robotics, or even from some other groups. It's not the same. I will tell details tomorrow. That my view from ITS perspective, how we look at it, intelligent transport system, the future to a higher level automated driving. So from IEEE side, you see there are many societies, councils, there are some overlaps, quite topic, but you can also see I highlighted in the three yellow color, education, social implication of technology, also technology engineering management. So they're not a pure engineering or technical oriented. They also cover some social science, education, other aspects. And every society, similar as my society, Intelligent Transport System, I know some of you are members of our society. So we have conference, standards of membership, education, technical activity, some young professional events and publications. So similar format for every society. And tomorrow I will go to details. It's about, I've been working for R&D many projects in Europe. So for me, it's just we look at the trends, what we're doing. In Europe, we do R&D project. It's always triple helix, academia, industry, and very often authorities also involved. It's not just a research. We always run a demo. That's the very challenging part, we all know. I started my PhD in 2002. So in Europe, we do a PhD as a job. It's a researcher, it's not education. So when I started, I didn't involve in all of these listed, but some of them. So we are doing from the development to deployment. Of course, you first need a validation, and then to nowadays. I feel it's always this, today I think, not only today, this week, we're talking about is to think about what is new, what is to share some new ideas or your vision, or think about the future of research, think about the future deployment. Also, what is really needed in this sector to really is a higher level automated driving only from research perspective or from industry perspective, is a business driven or it is some policy obstacles, also standardization work. So I will cover different parts of this talk. So the details, I know there are many publications. I've been working for industry. Normally, the 3 books are related to my work on corporate automated driving, also on impact assessment. So impact assessment, one is how you assess safety of the vehicle, for instance. That's a very difficult part. So what method we use, and also how you aggregate it, really look at the social impact, environmental impact, and economic impacts. So those work also, we did a lot in Europe. Key results were also in the publications we have done together with all the consultant partners. And also, not only in Europe, also the US, also in Asia, different countries. And this has been presented by different, as the previous speakers also mentioned the automated vehicle. But when we talk about the business, it's always, they're full of uncertainties. We're still working on these things: technical performance, interoperability, infrastructure, and safety, also social acceptance, also legal and regulation issues. Also, if you want to make it really applicable, like a large scale, you do need a business model. So how we talk about 0 to 5. So my preference is that we stick always to which level we are talking about automated driving, automated vehicle. So tomorrow I will go to provide some examples about corporate automated vehicle, and also the deployment challenges, especially related to my some project recently I've been working in the R&D project. So I will cover some ODD issues, also what type of infrastructure supported automated driving. So I've been working for, let's say, 802, 11P in the past, but I also have been working for 5G projects. So a lot of interesting things. I know in Europe and in the US, we have different situation than in Korea. In Korea, you may implement something. Probably in Europe and the US, currently, we have some political challenges. So we can go to some details. Technically, we always can debate. I think that's a good way for us to do. I think that I end up here. Tomorrow I will go to the details, and I won't overlap anything here. And this is my contact. Thanks a lot.
Yeah, thanks, Dr. Liu. Yeah. We look forward to the main presentation during the main event tomorrow. Okay, so please be seated. So, yep, we have another presentations in the first keynote speech sessions. So our fourth speakers, we invite Professor Xiaopeng Li from University of Wisconsin-Madison. So you ready, right? So please be forward, and please welcome him with a big applause. Yeah.
Thank you. Good afternoon, everyone. 안녕하세요. This is the only thing I learned on the flight. All right, so it's very good to thank Jason, Brian, and everyone, and also thank all of you for being here. And I apologize, it looks like this version of the slides was a little bit dated. But I do want to talk about some of the topics about connected automated vehicles and how to use artificial intelligence to address some of these questions. And so I guess, we have already had a couple of presentations about, very nicely reviewed the subject matters, like, like technologies and from traffic to race car control, and also the standards. And let's just talk about the general issues on the connected vehicles. So I want to revisit the concept of connected vehicles. So when they actually started this concept actually that it was based on infrastructure and vehicle collaboration pattern. It's like an infrastructure side, you're going to have roadside units, whereas the vehicle side, you're going to have onboard units as well. So we have to install lots of those extra hardware to the vehicles and roadside to make them communicate, right? So that's actually one early concept. But later, so this is actually what have been deployed in the U.S. for this concept, infrastructure concept, and many of them are just demonstration projects, and some of them serve some constant operations of maybe limited fleet vehicles, and we have yet to see this kind of technology to penetrate to the maximum market penetration rate to impact every vehicle. And then people may ask, okay, this kind of infrastructure is not there yet. So how are we going to benefit from these technologies? And from some of the studies, maybe the penetration rate will impact the performance. So from the connected data perspective, later people explored other data sources. Some of the industry companies are also claiming that they're working on connected vehicles, actually. One way is like they install the sensors on the roadside, like roadside sensors, or some of them using drones and helicopters to collect this kind of data. Actually, we worked with FHWA and the Department of Energy collected some of the data with drones and helicopters, and just process. With today's AI technology, it's fairly easy to process this kind of vehicles, and you can get a massive amount of trajectories. And that, if that can be made in real time, that this can be served as a connected vehicle data. Some people call this as proxy CV. So that's an alternative. So this alternative only have the incoming stream of data, so extract the trajectory data from the vehicles, whereas it doesn't pass information to these vehicles. But at least you have data. And recently, people also talk about connected vehicles data in the concept of telematics data. So what are the telematics data? So if you have a production vehicle, actually, you will probably, if that's made after 2015, 2016 in the US, you'll probably send the data of your vehicle operation every like a couple of seconds. And these data could include very detailed information like VIN number, model, powertrain, class. Some of the private information may be masked, but you still get a lot of the vehicle-based information. And also the real-time information of the vehicle location, kinematic speed, heading, accelerations, and they also have energy level data, fuel, battery, and also ADAS activation, some alerts, ABS and collisions. I don't think they have a lot of sensor data, although some of these vehicles have cameras and radar, and some of them may even have LiDAR. But you pretty much see these are very common. And then, so some of the state DOTs in the US started to ponder which way we wanted to go. Will it be like infrastructure-based or proxy CV or telematics data? Actually, I actually have been talking with those different states in the US. Actually, for example, Utah is going with the infrastructure-based manner. So they have made lots of good, successful deployments and have used these facilities to supply their fleet operations. And Indiana, which is another state in the US, they may want to go to the telematics data because actually there are already some active vendors in the market providing this kind of data with a reasonable price, I would say. In the nice sense, you can get 6% of the market penetration rate from one company. And also, maybe if you combine different companies together, you'll get the very rich data, like over 10%. So and this is going to be the application done by scholars in Indiana, and they were looking to the offline data and try to, like use this probable vehicle type of telematics data to analyze the incident. You can put that into real time and to really understand what happens in traffic. And if you can successfully pass that information to general drivers, you'll be able to put forward some of these warning informations to prevent accident. And if you send that information to automated vehicles, you can facilitate the CACC and eco-driving, this kind of applications, I would say. So I'm not going to talk too much about the math and animations and also field experiments, but I just want to give you a heads up about what I'm going to talk about. So we're going to talk about history, development, in the past, what kind of physics model people have developed, and then we're going to talk about learning, and then we talk about integrating physics and learning to actually analyze this kind of data and having a good understanding of the traffic environment. Then I'm going to talk a bit about automated vehicles, and we know that there are already lots of commercial companies doing automated vehicles. Many of these are just passenger cars, but you see other modes of transportation, small shuttles, trucks, and like delivery robots, and some hotels or restaurants may have this kind of robots, okay? So I just want to say, autonomous vehicle, it may appear like an old new concept, but maybe people working at us have seen that a lot. And as a result, we have in the U.S. actually 92% of newly produced vehicles in these years have a trim with level 1 or level 1 automation. 50% of them having like a level 2 automation. They're running everywhere actually. I have a Tesla actually with full self-driving. I don't know. Full self-driving. It's really not full self-driving, but I experienced this, and just like some of you mentioned, like Dr. Liu mentioned, how this vehicle is going to impact the traffic. How are you going to understand them, right? So, some of these understandings are based on like anecdotic stories and like market stock performances and some one incidents here and there. But how do we comprehensively understand it? So it's something we want to talk about. Right, so we could utilize those different data we collected and to evaluate the performance systematically. We can have more quantitative understanding and scientific understanding of their performance. And also, this is followed by Dr. Park's study, like we have a vision of cooperative driving automation, like having all these vehicles not only driving autonomously, but also connected and work with each other, like having platoons and having eco-drivings. And we want to push the transportation system from individual vehicles benefit to the system optimum by setting up some cooperation strategies. And in this part, I'm going to talk about reinforcement learning, and that's what we did before. And also recently we started to look into the foundation models or large models. The reason we want to look into it is because the companies are moving towards these directions. If NVIDIA and Tesla, have already started to use large models to guide these vehicles, and they're going to perform differently. And maybe how we're going to capitalize on this development and try to realize the vision of cooperative driving automation. So this is pretty much about what I plan to talk. And I'll just give you a heads up here, and hopefully I can show some of our modeling, math, as well as field studies tomorrow. Thanks.
Thank you, Professor Lee. Well, actually, our title is about the 5G connectivity and that based automated mobility. So the wordings you probably hear so frequently during this event is connected and cooperative. So please be connected and cooperative, get it to each other. So during this event. Okay, so this is the end of our first session, and then gonna have a 10 minutes of a coffee break, but actually during that breaking time we're gonna have a photo time, and we're supposed to have just one shot, but just wanna recommend another shot with everyone here, if that's possible. So please, everyone here, including the audience, so please come forward and gonna have a first shot, and then with just the guest speakers, we're gonna have a second shot. So please come forward to the podium. Yeah. So let's welcome the first speakers in this session. So the first session is starting by Professor Junseok Oh from Western Michigan University, and he will supposed to talk about some Michigan story about cabin, right? So presentation. So yeah.
Should I do all over again? Okay, hello everyone. My name is Junseok Oh from Western Michigan University. So I'm from the civil engineering, and I'm also director of Transportation Research Center for Livable Communities, which is one of the Tier 1 University Transportation Center established in 2013 by the US Department of Transportation. And then as you see, our center aims to support development of livable communities through integration of advanced technology. I am very pleased to have the opportunity to share this. This actually a presentation. So my talk is, as a civil engineer, is mostly about roadway infrastructure, how we are integrating into our transportation systems for autonomous vehicle. So this is one I showed you, but actually the Brian Park already showed this one. Of course, the probably dream of self-driving vehicle has a long history, right? So perhaps the first autonomous vehicle might be the Aladdin's maybe magic carpet, right? So probably magic carpet might be one of the most the first one, the flying carpet, and then actually taking the person to anywhere they want to go. And then the image in here is actually a driverless car of the future. And then it was in 1950s, long ago. So we have been doing a lot. Since then, there have been many the attempts to develop autonomous vehicles, and also that are very successful. The field test taking place mostly in 1990s and 2000 and later on. And then this is actually a future vehicle, but I don't think it is a future vehicle anymore. So that right now, all these advanced features like adaptive cruise control, automated emergency braking systems, lane departure warning system, and then automatic lane keeping parking systems, all these things. So probably many of your vehicles might already have those features. This is not any longer future. It is actually already our present reality. So autonomous vehicles are already available in various forms. And then companies like already Waymo and the Cruise in the United States, and Baidu and AutoX in China, those are companies already leading the way. And then Waymo, for instance, offers the ride-hailing the services in Phoenix, in Arizona, and San Francisco in California. So, however, there have been some significant failures. In May 2019, a self-driving Uber vehicle in Tempe in Arizona struck and killed one pedestrian. And then it was the first fatalities involving autonomous vehicle. And then the incident, of course, raised serious concerns about the safety and also reliability of self-driving vehicle at the time. Actually, I supposed to show the video, but anyway, it's already done. Okay, so those are actually the images. And also, wrong way was another concern. So there have been incidents involving Waymo driver taxis navigating incorrect in California and also Arizona. So in April this year, and then in San Francisco, the vehicle was moving wrong way. And also in the June 19th, the Phoenix, the Arizona, the work zone, the vehicle was moving wrong way, and then taken by the police officers. And also August 24, in Arizona, actually at the intersection. The vehicle was not able to get in the right direction. So those are one of the actually many cases with having some complex environment causing some confusions of those actually Waymos and other autonomous vehicles. Perhaps autonomous vehicle is one big market, and then the vehicles are operate independently using internal the sensor systems. And however, the connected vehicle system is another actually movement. We have been doing a lot of research. And then although autonomous vehicles aims to develop a self-sufficient vehicle without infrastructure or any assistance, however, there are two systems, of course, is combined, and that we now called connected automated vehicles. But I'm not sure whether they are well connected, but those actually are U.S. Department of Transportation's main the stance, and as of now. So in the United States, of course, in order to get a connected vehicle system, the dedicated short-range communication has played a key role for past couple of decades. And then for the vehicle-to-vehicle and vehicle infrastructure communication. But it has been a core wireless communication systems specifically for autonomous vehicles and safety applications. But however, as a demand of the vehicle to everything, communication has been growing market, and then cellular-based communication system has been actually evolved. So-called the cellular vehicle to everything technology has been now becoming one of the key elements. Recently, the US DOT has established a set of the short-term and mid-term and long-term the deployment goals to focus more effort in the coordinate actually the actions. And then by 2036, US DOT plans to fully deploy vehicle to everything across the national highway system, and also plan to enable the VTX at 85% of signalized intersections in the top 75 metropolitan areas, and plan to achieve 50 interoperable the cybersecurity developments will be actually in place. That's the actually plan. So we want to see how it goes. At the same time, I mean, actually, a lot of billions of dollars has been invested to in-vehicle technology for autonomous vehicle, including ADAS and the fully automation driving systems. However, small fraction of money has been spent on developing infrastructure to support and enhance advanced road. And also, many people are arguing that, hey, probably smarter vehicles need smarter roads. And a smarter road also need so actually stronger partnerships. And then in July 22, in Michigan, actually the state of Michigan enacted a national first law authorizing automated vehicle roadways. And that allows private companies to deploy the next generation transportation infrastructure technology. And then so-called Cavenue is one of the startup company at the time. And then they initiated so-called Cavenue connected vehicle actually corridor in Michigan as in I-94. And this was the infrastructure invention that they are trying to. So Cavenue is interestingly a private company, and then launched by the Google parent as Alphabet Sidewalk infrastructure partners. That is one company. And then the company, the mission is to build a world's most advanced road, and also approaches to create the digital model of the roadway, and also trying to make the physical infrastructure. So basically, digital infrastructure and also physical infrastructure, they are trying to deploy those to help autonomous vehicles. So basically, combining digital infra and also physical infra, and then they are trying to collect data from multiple data sources, and also generating meaningful data to send for road users and operators. And also the physical infrastructure is to benefit connected vehicle performance, and also providing better lane geometry and also physical lane attributes. So as of now, there are two main activities going, and then one of them is I mentioned to you in I-94 in CAV corridor in Michigan. It is actually fully a dedicated lane. So initially, they plan to have 39 miles between Ann Arbor to Detroit, and then it is a fully dedicated lane. I mean, at this point, they had a 3-mile testing field already started last year, and then they are beginning collecting data. That's one activity. The other one is in Texas, 21-mile segment with the speed limit of 85 miles per hour is equipped with sensors for autonomous freight corridor. So that corridor is designed to probably truck platooning and also autonomous trucks in Texas. So interestingly, this effort is by a private-driven effort, and also Kavin is one of those cases. Probably this may actually expedite deployment of the cellular V2X, and also its business model is something interesting. I mean, I was trying to figure out how they are going to the business being more sustainable. So they are arguing that they are trying to collect user fee and also a subscription fee or payment by actual performance. So that's what they are thinking of. But still, I mean, I'm not trying to promote actually revenue. I'm just raising those issues, how we can incorporate such effort to help autonomous vehicle in the future. Probably maybe during our X-Day session, during the days, we can talk about the more details, what will be a future will look like. So that's the main point that I want to discuss. Thank you.
Thank you for sharing the Cabinet project. Well, it seems very soon people will make a plan to visit Michigan to see this Cabinet Road and what kind of things to be implemented here. So thank you for sharing the project. Okay, so let's welcome our second presenter, the Andrea Malikopoulos from Cornell University. So he will talk about the combining learning and control in emerging mobility systems. So please give him a big applause. Yep.
Can you hear me well? Great. Thank you, the organizers, Professors Jason So and Brian Park for inviting me to be here, and thank you all for coming. Actually, today I'm going to talk on a different topic. My initial talk on combining learning and control will be on Thursday. What I thought to do today is just to introduce some test beds that we have built in order for us to help us study and push some technologies in the area of connected automated vehicles. And in particular, I would like to introduce a smart city testbed that we have built in order for us to be able to do some testing beyond simulation. So in my lab, the Information and Decision Science Lab, we develop theories and control algorithms that can make cyber-physical systems able to learn how to interact with the environment. The focus, a significant amount of work is focusing on emerging mobility systems and how we can use connectivity and automation to improve the efficiency in transportation. So we have built a scale smart city. This is 20 by 20 feet or 6 by 6 meters long. And we have, everything is in scale of 1 to 25. And we have built about 75 robotic cars on these scales, 1 to 25, that we can use in order to replicate any transportation scenario within an environment that can help us do some testing. So we have, we can use these cars, we can use drones that can help coordinate the cars and exchange information. We can replicate any scenario that we can possibly have into the city. We can have, we can replicate concepts on first and last mile delivery between ground vehicles and drones. This is an example that the drone is supposed to pick up a package from the building and then coordinate with a ground vehicle to drop it off and so forth and so on. We have integrate driver emulators with these robotic cars so we can drive these little cars and can replicate human driven, mixed traffic environment when coexisting with human-driven cars and robotic cars. So in this case, we have a little camera in front of the car, and the driver can see through a monitor the conditions, and then they can interact with other cars. So if you can see, I mean, I'm not sure if you can see, but the camera is located here in the car. And through the camera, the driver can see and replicate. We can use this testbed to have cooperation between ground vehicles and drones. This is the case that we have a platoon of vehicles and drones which collect information from the environment and then report back to the vehicles, and then they can cooperatively achieve a specific mission. We have also created a digital twin of this city. That was something that we did overnight during COVID period, since we didn't have access to the city. And then my students thought to replicate, to create a digital twin. So essentially, we can use this with our collaborators. They can implement their own algorithms, and then once this becomes mature, they can come and do experiments in our physical testbed. Actually, as we speak, we're working on making this testbed remotely accessible to everyone who wishes to do an experiment in our scale city. So you can create an account and then do an experiment by using both the digital twin and the physical testbed. We also created an app that can replicate shared mobility like Uber and Lyft. So if you come to our lab, you can download this app, and then you can call any of these cars to come to your destination in the city, and then you can assign an artificial destination, and the cars can take you to this destination. And of course, you might think that this doesn't make any sense, but the way that we have implemented this platform is for us to validate some of the optimal routing algorithms that we develop. The city was featured in the IEEE Control System magazine recently, and so if you are interested in learning more about the technical details, how we have built the infrastructure and the cars, we can look at the article in the magazine. We have also a simulation testbed. We use commercial software and open source software that can replicate any of the cities that we want to study. And more recently, we built up a virtual reality simulation testbed where somebody can wear a headset and can, be in a virtual environment that can interact with autonomous cars. So the driver is sitting in the cockpit, and then, as you can see, he turns the head around, and then he can see the interior of the car and also the virtual environment with other vehicles, pedestrians. This can help us validate some of the safety control algorithms that we develop in the lab in an environment that can help us do some experiments otherwise would be almost infeasible. We also recently bought some agile limos, autonomous cars. These are fully autonomous. We can use these cars for other type of experiments that includes coordination. These are a full-scale, they have all the capabilities of a full-scale autonomous car in a scale environment. It is about 1 to 10th scale. And then we can help us, validate some of the control approaches that we use in the lab towards improving safety and also efficiency in transportation. So the whole idea for us was how we can develop control algorithms that can coordinate vehicles in scenarios that there is a potential conflict. And for these reasons, we thought that going beyond simulation is critical. At the same time, we can't really do experiments in field testing experiments with real vehicles due to the safety constraints and other cases. So I'm going to show you some experiments that we have done using the scale city. This is one experiment of a fully autonomous intersection. You can see how the cars can coordinate and cross the intersection without stop-and-go driving and without collision. We have extended this to a roundabout. That's a similar case. This is the baseline scenario where the cars have no connectivity or automation. This is a scenario that all the cars are connected and automated, 100% penetration. And you can see how, in this particular case, you have stop-and-go driving and queues accommodated from the cars, although in this scenario, there is a smooth traffic without stop-and-go driving, without congestion. That's what you want to replicate. And then you can take these trajectories and feed them to appropriate models and get quantitative results about energy consumption, travel time, and so forth and so on. This is another example that my students are getting creative at some point. So they replicated the phantom traffic jam in the roundabout. That's the famous, but I think they put so many cars, which essentially you can't really sense the phantom traffic jam in this case. I think they should use a couple of less cars. This is the coordinated scenario in a corridor. You have intersection, merging roadway, and also roundabout, and you can see how all the cars can smoothly coordinate and cross these scenarios without stop-and-go driving and without creating congestions. These are the three main areas of potential conflict. This is a scenario that we test. We use the scale city to create platoons of vehicles, and at the same time we can track the trajectories of the vehicles. So essentially the scenario here is that this vehicle will start deriving an acceleration, appropriate acceleration, so that they can form a platoon of vehicles following up. This is the case that we want to form intensively platoons that can, and then use the coordination scenario that we have developed to coordinate, instead of individual vehicles, but now platoon of vehicles. We have used also the scale city to do intentional crashes between the cars. So we have bad actors or bad drivers in the city, and then they drive in a way that can cause crashes, and then we look at this car, and then we use these scenarios that can validate some of the algorithms and see how can potentially avoid these unexpected events of the cars. So as I said, the scale city is a helpful tool for us to use, do experiments without spending too many resources, and without having safety concerns. This is a scenario with a human-driven car. So we have the human driver, drives throughout the city and be able to see the environment through the monitor. We have also developed driver assisted scenarios. This is a scenario with a human-driven car interacting with autonomous cars. So this is the human-driven car, and as you can see, intensively will drive in a way that we can test how the autonomous cars in the field will respond to this driving behavior. So this is the human-driven car. It's about to cross an intersection. The other vehicles are fully autonomous and connected, so they're supposed to cross the intersection without stop-and-go driving. But then the car will intervene in the intersection, and everybody will stop and wave and yield to the human-driven car. So this is the kind of scenarios that we can use in our scale city. We also have the drones, and we can use the drones as coordinators in the infrastructure, as the infrastructure is a flexible infrastructure that can collect information and data from the vehicles, and then spin back other type of information, and this information can be used by the cars to cross the intersection without stop-and-go driving. So we call these drones acting as coordinators. For example, the scenario here is that if you have a big game with a lot of people that you want to evacuate this and navigate all these fans out from the field, then you can have coordinators that can fly around the field and then coordinate the evacuation of the city in an efficient way. We also use the drones for other decentralized control approaches that we develop in the lab, and how you can do formation using connectivity between the drones. So this is the scenario with a digital twin that I mentioned before. We have 6 vehicles crossing the roundabout. As you will see in a while, we can replicate this scenario precisely in the digital twin, and then having the same sort of scenario in the physical testbed and also in the virtual environment. We have used the knowledge that we learn in this scale city to field testing in M-City. We had recently completed a project from ARPA-E that the goal of which was to improve the efficiency of an Audi A3 plug-in hybrid electric vehicle by at least 30%. So we develop all the control algorithms first in our scale city, and then we move them to M-City, and we did the test. Perhaps you are aware that M-City has the augmented reality, so the Audi is in the field and then interacts with the virtual cars. This is the baseline, the coordinated scenario where all the cars are connected automated, and you can see how come the Audi crosses the merging point. This is the baseline scenario where there is no connectivity and automation, so the Audi is blocked by this black vehicle, virtual vehicle, and avoid, and create stop-and-go driving. We also did some testing with the Audi in the chassis dyno of our industrial partner, Bosch. I'm going to speed up just, for the sake of, for the interest of time. And we show some improvement in energy consumption. This is the new scale city, version 2 that we developed at Cornell, just finished up a couple of months ago. The new feature is the cars, so we have more advanced cars right now in the city, making in total 75 cars. And we have also, this is one of the scenarios that we have developed. We have also now 6 driver emulators, so we can have up to 6 human-driven cars in the city interacting with the other cars. So this is a scenario of the human driver. The human driver, I think, is this car, if I'm not mistaken. We'll see. Oh no, this is the car. This is the human driver. Again, trying to act as a bad actor and getting in front of the intersection, and you can monitor what's going on with the other cars. And this is a full coordinated scenario that we have developed in our new scale city. I'll have more technical discussion about the context and how we use the scale city tomorrow on Thursday, in our talk on Thursday. I need to acknowledge all the financial support from our sponsors. And with this, I would like to thank you for your attention and take any questions perhaps on Thursday.
Thank you very much, Professor Monica Pose. So actually in Korea, the research about testbed and the digital twin, that's one of the hot topics in Korea as well. So probably be a very great reference for many researchers here. So I look forward to the next presentation on Thursday. Okay, so let's go on to the next. Third speaker here is Professor Simeon Calvert, Delft University of Technology. So Professor Calvert will talk about beyond engineering and breaking interdisciplinary insights in automated vehicle development. So please give him a big applause.
Thank you very much. It's an honor to be here, today I want to focus a little bit on AI versus control and traffic theory. Yeah, so just to give a quick introduction of who I am first. So I'm Simeon Calvert. I'm an associate professor at the Delft University of Technology. I'm the director of the Automated Driving Simulation Lab there. I also co-direct the City AI Lab for the behavioral urban analysis. My main focus within my group is on the impacts of automated driving, and especially on the impacts on traffic flow and traffic safety. So we're looking at many of the interactions that we expect within traffic and see what the impacts could potentially be with current but also future forms of automation and connectivity. And we're also very open to collaboration, and we believe strongly in synergetic approaches to research. So we perform quite a lot of research with many other partners, and if you want to get also involved with us, then also feel free to talk with me. Within my lab, we've got 4 different main themes of research that we work on. One is on traffic dynamics impact assessment. So this is looking at what are the impacts in practice. The second is on responsible control of automated vehicles. Thirdly, on acceptance and trust of CAVs. And on the simulation side of things, that's traffic and also driving simulator work we do. So to come back to what I want to have a chat about today, is when we've got AI, do we actually need physical models? Do we need control and traffic theory? Now this deviates a little bit from what I'll be talking about later this week, but this is a topic which I think is important, especially in this domain. It's been touched upon already by a few people here, because AI performs really well in many different situations. It's very good at processing a large amount of data in complex environments and coming up with solutions that many of us and many algorithms are not able to do. It's adaptive, and also when we combine it with the sensor options that we have, it gives us a lot of options for decision making. And many OEMs, and again this has been touched upon, are increasingly making use of this technology. This exists within our sensor technology, it exists within many of the vehicle control technology which are on the roads. So with many of the ADS and ADAS systems that are being developed and are being implemented at this moment. So is it then wise to just completely rely on AI? Well, there are a few things that AI also struggles with. Managing edge cases, for example, situations that don't often occur. Now, you probably don't have many lions on your roads here in Korea, and certainly in the Netherlands we don't. But this would be an edge case. Now, there are also maybe more realistic edge cases you can think of, such as a sensor viewing a reflective surface. Now, I know this has happened a few times, that a vehicle thinks that another vehicle is approaching it. Well, it's just seeing a reflection of itself. Now, these are edge cases that don't occur often, but will affect the way a vehicle drives. And AI struggles with this. Maybe also interpreting complex human interactions. So we see here an interesting situation, especially when we look at vulnerable road users, so pedestrians and cyclists. This also throws up some difficulties. Maybe also knowing when to relax strict regulations. So when does a vehicle, when is it permitted to cross a line, or when is it permitted to do something which it wouldn't be allowed to otherwise? Now, as humans, we have an idea of when that would be appropriate. Maybe an automated vehicle doesn't, and this is something that we have to consider. So if you consider the different traffic scenarios that we have, many of the most frequent scenarios, so for example, car following, is on the way on the left here. These are situations that occur often and have a high frequency. And the less likely ones, the edge cases, are on the left-hand side. And these are situations that don't occur often, but there are quite a lot of them. Now, AI is very good at this left-hand side, the situations that occur often, are frequent, and can be trained with a lot of data. We struggle a little bit more on the left-hand side, where situations don't occur as much, and there's not much data to train off. Therefore, this is where AI struggles a bit. And industry recognizes this, so this is also where we're looking at alternative options as well. What could be some of these alternative options? That could be a hybrid approach that combines basically the strengths of much of the physics-based approaches, the traffic and control theory, but also the strengths of AI with the data learning, also the adaptability there as well. And with connectivity, one single vehicle is not just collecting data for itself, it's also collecting data potentially for a whole fleet of vehicles. So this is also where there's potential benefits. So to touch a little bit on, firstly, some work that we've been doing in Delft, and this is more on the theoretical side. But this focus is on how can we start to include human cognition in simulation models. Because what we've found is that once you start comparing automated vehicles and human-driven vehicles, especially in simulation, they're both basically algorithms. So one is rather robotic and so is the other. So we've been trying to improve our human-driven vehicles by adding a cognitive layer. So basically, so that the vehicle drives as if it's a human being in the simulation environment. And this throws up some interesting dynamics. So here we have an example of vehicles driving down the way, and there's been an accident here. And we're modeling the vehicles driving up the way. And there's no physical constraint there, no capacity degradation. But what we have been able to do is, using this cognitive layer, add an extra distraction to these vehicles, that distraction of this accident here, so that they are slowing down even though there's no capacity constraint. And this is due to the model using task demand as an input for driving performance. Now, I'm not going to go into this in detail at the moment, but this just demonstrates that the cognitive layer here improves the traffic performance, certainly if you compare it to a real a human-driven vehicle for simulation. Now, why am I highlighting this? I'm highlighting this because also when you look at the hybrid models, this is an example from Cognibit that I came across recently and I was allowed to use. This is a company that tries to build hybrid AI physics-based models, and they do this by basically capturing the structure of what they're trying to model. In this case, they're trying to model a human-driven vehicle or an automated vehicle, and they're doing this based on many of the same cognitive processes here. So we perceive, we think, and we act. Obviously, as part of that, we have our attention span, etc., and we make decisions. Now, I can go through the whole thing here, but this is a structure which is based on cognitive science. Now, instead of then going deeper into cognitive science, in each of these blocks here, what they do is they run AI models that uses the strength of the AI to capture the best possible outcome for the way this vehicle would act, but in the structure which is based on theory, on, in this case, cognitive theory, but this could also be connected to control theory as well. And doing this, what they're aiming to do, and this is also what the premise here is as well, is that we're making the transition from a rule-based approach to a data-driven approach in which AI is doing great, but is missing many of the tails and missing many of the edge cases, to an integrated approach which uses the AI, the data-driven approaches, but also is using the structure of the system itself. So in this example of the cognitive system, which then takes us further into many of the edge cases. Will it get all the way to every single case so that AI can work on its own? Probably not, but it certainly takes us a big jump forward. So this premise, therefore, is, do we need traffic and control theory or other theories when we've got AI? Yes, but we probably can also take a step further and try and integrate much of this as well. So just to highlight a little bit of what I want to talk to you about in the coming days, my presentation for tomorrow is going to be on transdisciplinary design and evaluation of automated vehicles. Automated vehicles are expected to have a lot of benefits, but they're not fail-proof. So accidents still occur. This was highlighted in one of the previous talks. There's responsibility and liability issues, and also control issues, and also some societal challenges in regard to acceptance. Now, we're looking at meaningful human control as a concept that allows many of these challenges to be tackled. Once control, but from a meaningful perspective regarding human interaction is included, we see that we can have a full chain of control over a vehicle, from both close to the vehicle and the user, but also from a regulatory or societal point of view. We can involve all stakeholders within this, and we can also consider if the vehicle itself can consider the intentions and the reasons of the driver or the users as well. So we have this connection between the users and also the automated vehicle development. So this is very applicable for design of automated vehicles, but also for the evaluation. So this is something I want to talk about more in the upcoming BrainLink Lab Day, which is tomorrow for my session. So thank you for your attention, and I hope to see you there.
Thank you. Thanks for the presentation, Professor Calvert. Our schedule is a bit the next presentation right away. So Dr. Randall Rubuck from Omniair Consortium. So he's going to present about the CV2X communications panel. So please give him a big round for his presentation. Yeah.
Hello, thank you very much. I lead the technical activities at Omniair. And I've been in the V2X communication since 2004. Started with DSRC and 802.11p. And my goal is not quite research, but it is going to deployment. So one of the key things here is make sure that we can trust the V2X communications. So I've spent many years doing RF technologies. I got a vast background in RFID tolling, which is used in many different countries. And my talk tomorrow will deal with Omnier certification, give you an introduction and overview. Also talk about trusted communications, interoperability, and industry cooperation, which we need. And then they've also asked me, what do we think the research needs are for the V2X technology and its deployment? Omnier was founded in 2004, started with the RFID tolling, have migrated to the V2X communications. I spent in DSRC in the late 2010 era. I think I authorized 5 test laboratories, 3 test tools, and probably about 10 different devices here in Korea. And here we have some members that have invested in V2X certification. We have Cecil Tech here that does the SCMS security credential management and its testing and validation. We have IT Telecom here, which was our first OBU and RSU device certification in the LTE V2X, which we call R14, or direct V2X. The US DOT and its deployment plan, which we'll cover tomorrow, they talk about 2 different items. One's direct V2X, which gives you very high latency, so you can actually do intersection collision type warning, or which we call red light warning. And they also have network V2X, which is don't need the so-called the super sensitivity of latency to do things on the road, such as the traveler information message, weather warnings, and different things like that. So we've got to use our spectrum, which in the United States is the FCC, what they give us, and make the technology work. We're hopefully waiting on the second rule and order in the United States to proceed farther, and we expect that any day now. So we have about 90 different members covering all different areas, from technology providers like Qualcomm and Autotalks, to device suppliers who use that technology to integrate it, test laboratories such our current LTE V2X test laboratory, TTA, has done a wonderful job here in testing devices. We've been given certification from that perspective. We also have test equipment folks such as Waities here in Korea, and different agencies and firms in deployment. We do have a MOU, or a memorandum of understanding with ITS Korea. And then our job is to certify connected and vehicle and tolling technology to ensure the devices conform to the industry standards and have interoperability. There's functional interoperability and there's application interoperability. You can see that we went from DSRC to C to V2X. In RFID tolling, we went from single protocol to multi-protocol. In the United States, we have 3 different protocols that works across our country. We have working security to SCMS and certificate replenishment. There's a standard called IEEE 1609.2.1 that basically gives multiple SCMS providers a way to participate in all deployments, have interoperability, and also replenish certificates in the field. Some of the elements and benefits of trusted V2X communication. Your device certification should be the cornerstone for an agent's procurement strategy and addressing electronics, which I call Electronics 101 and V2X 101. We see a lot of different devices and tools. We know how they behave. We want everybody to behave towards the industry norms. And so we want to do that job so we can allow the agencies apply it, so-called in applications, because that's really what they want to do, to basically take the technology, make it beneficial in their regions and areas. Second bullet is applying the appropriate level of testing as far as verification, validation, and certification. Not everything out there needs to be certified, but there are some key aspects where it's over the air that must be done so we have communications among all vehicles and the infrastructure. So we have put a definition of what a certified device is, which is basically been certified by a third-party certification body, tested by an independent accredited lab using qualified test tools to validate test cases and specifications. Our members go through the standards, look at the key aspects, generate test cases, which we apply into a certification scope. I'll also be talking about the V2X sensor for communications for their intended roles and benefits. One of our problems 20 years ago was we tried to make the V2X technology to do everything and be foolproof. We need to use the communications, what it's meant for, and have the other sensors do their job, and we'll bring it together so we have automated vehicles with connectivity. So use the V2X for communications, and we'll get to deployment a lot faster. We do need industry cooperation, collaboration. There's many different groups. There's the 5GAA that's working the marketing and other aspects of V2X communications. Omniair is the group that's kind of doing the testing, conformance, and certification portion of it. We do have the government or the US DOT role in this. We also have the standards groups, the SDOs, such as these standards. Most of them come from IEEE or SAE. And far as the protocol technology. We do hold V2X technology readiness testing events. We just had one in San Diego about 2 weeks ago, and IT Telecom and Cecil Tech were there. We had a lot of folks, and we're all working towards deployment, and the US DOT has 3 acceleration pilots they're moving for, and one of their key aspects is interoperability. They've had a lot of different technology sub-pilots out there, and they found out that those devices aren't working into the other pilots, and this technology needs to be done. We had a plug fest in Taiwan the end of last year. Had a lot of people, a lot of interest, and I believe ITS Korea, which is I believe giving a presentation later this week, had a plug fest here in Korea for the Korean folks, and they invited Taiwan. It only helps everybody, and since Taiwan and Korea are using the same standards that we're using in North America, that's one of the collaborative efforts. Our process does allow regionalization of some of the technology. So we're working this to have successful deployment. The VDX role in automated vehicles, talk about security, privacy. A lot of it's already built into the standards, and we're in really good shape on this. When I first started, all they could talk about is privacy and anonymity. We got it covered. We're a lot more trusted and safer. If you're worried about your privacy, don't carry a credit card, don't carry a smartphone, because that's a much easier way to get that type of information. We do need some industry, academic, and government research to continue and deploy V2X communications. Thank you very much.
Okay, thank you for the presentation, Dr. Roebuck.
It's not doctor.
Okay, Mr. Roebuck. Okay, so now we had our board presentation in person, and our actually last presenter is Professor Tommy Spenson from Chalmers University of Technology, but he actually couldn't make it in person here, so that's unfortunate. But instead, we have a recorded video from him, the message from him, so we're gonna have this video for his presentation.
Thank you very much for inviting me to the 2024 BrainLink X Lab Day and this talk concert. It's very pity that I cannot join in person, but I'm very happy that I can contribute digitally. So I will talk about towards sustainable mobility with 6G mobile communications. And Chalmers and my team have been very active in the European research towards next generation mobile communication systems. In my case, all since the 4G times. So in the fourth generation mobile communications, we enabled a mobile internet with rich multimedia. In 5G, we worked further on densification and using upper frequency bands in the millimeter wave spectrum towards high speed and high capacity mobile internet. We also enable massive machine type communications to at scale support wireless Internet of Things. And in particular, we worked on robustness and low latency capabilities towards Internet of Skills, which enable, for example, remote driving of driverless cars. And it's ideally, the goal is also to enable advanced cases like remote surgery. There's still some work to be done here, but the pieces are there in the 5G standard. So one thing that we worked on quite carefully in the 5G times was to support vehicle to everything with the mobile network, so-called cellular vehicle to everything communication, CV2X. With CV2X, we connect other vehicles, we connect pedestrians and cyclists with our smartphones, and we connect the road infrastructure. And this we do by the mobile network that it can enable guaranteed coverage and the continuity of services. So in one of these EU projects, the 5G car, we worked on various use case classes: corporate perception, corporate maneuver, corporate safety, remote driving, and autonomous navigation. Still, I think there are quite many more things that we can do with the mobile network. In particular, if we view the vehicle not as a smartphone on wheels, but rather as an advanced cooperative node. There are potential mutual benefits: better mobile networks efficiency, because vehicles can collect the context information to improve resource allocation efficiency in the mobile network. Vehicles can share route information to the mobile network for proactive resource allocation, don't transmit receive beamforming. Vehicles can act as moving base stations, and In turn, the vehicles can get more reliable and secure access to V2X services. More efficient network-assisted V2X improves scalability, reliability, range, and information horizons. More accurately connectable by road users, such as pedestrians, cyclists, pets, to traffic safety efficiency protocols. Mobile networks assisted based radar sensing, and this is getting more and more important because vehicle-based radars are starting to interfere, and there's a need for coordination. And we can also enable more efficient and reliable mobile edge computing. In addition, there are an opportunity for new disruptive business models here, and especially because vehicles are continuously sensing various kind of information in the city, so they can help a smart city other functionalities. And they can even potentially act as micro-operators for moving base stations. In the 6th mobile generation network that we are working on, we started in EU in a flagship project called Hexa-X in 2020 that finished in the summer last year, and we are continuously working now in the follow-up project Hexa-X2. Here we define the 6G as a convergence of the digital, human, and physical parts of our world, and there are 3 pillars: trustworthiness, digital inclusion, and sustainability. If you do this right, we can also create an internet for society needs and help to fulfill the United Nations sustainability goals. And there are 17 of them, and we have done an analysis within Hexa-X project, and most of them mobile communications can help. They have the same target date, 2030, for both the United Nations sustainability goals and the 6G mobile communications deployment. From a technical perspective, we see a convergence of communications, sensing, computing, and storage with AI. And by doing that in a clever way, we can create an Internet of Senses that enables authentic remote participation and interaction. But to do this in a sustainable way, we need to adopt holistic performance metric that calls for holistic design. So a quick glimpse on the radio enablers we are working on, all leading towards densification and integration. To start with, we are looking into other frequency bands between centimeter wave and millimeter wave bands, and we are looking at sub-terahertz bands, we are looking at visible light bands, and we are particularly looking on further densification in the spatial domain with massive antenna systems at both ends. We're looking into other kind of deployment and enabling technologies for antennas, for example, reconfigurable intelligent surfaces. We also looking into different ways of distributing these antenna systems in so-called DMIMO networks. This densification needs efficient backhauling, so we're looking into set backhauling. The densification also calls for more integrated mobility support with spiked handovers and similar techniques. And we need to support this digital coverage also outside of the cities. So vertical convergence is getting more and more important. And this is especially true for cellular V2X services. Here we see an opportunity for combining various frequency bands, especially free space optics with millimeter wave bands, especially in the LEO satellite links. We also see a further convergence in the network from the access to the backhaul fronthaul over to the transport networks in what we call network slicing. And we look into the opportunities to use location and context-aided information to boost communications. And then, as I have mentioned, the opportunity for doing sensing to assist communications, and also communications to assist sensing. So we see an opportunity here to integrate those in different levels in the mobile network. One example of how we can use context information is dynamic blocking avoidance. If the vehicles can share location information, they can share their trajectories and their speeds, we can do proactive resource allocation here to avoid blockers, for example, with cooperative base stations or by using this kind of reconfigurable intelligent surfaces. We also see an opportunity here for collecting this kind of information from vehicles passing by and using that in a digital twinning map. And also proactively, we have measured different communication properties and stored them in digital map. And this information we then use for assisting communications. And it can also be used for visualization and decision support for smart city monitoring and planning. So some take-home messages. 6G integrated sensing communications, ISAC, seems promising to support 6G CV2X services. Context-aided communications aims to enable dense and reliable communication with reasonable overhead. RF digital twinning might be useful for static a priori context information. And integrated sensing seems very promising for acquiring dynamic context information. So thank you very much for listening. And I hope to see you in person soon.
Thank you, Professor Spencer. I hope he listened to this. Okay, so this is it for the presentation, and we're gonna starting the discussion session. But let's have just 1 minute, a very short break for set up the table. So 1 minute.
I was told to moderate this discussion session. So if there's a question from audience, now is the time to raise your questions, share your questions. If not, I'm gonna give a heads up to the distinguished guest speakers. I will probably ask about 3 things: technology, business, and acceptance or trustworthy. So if all of you can just talk about your understanding of technology challenges or possible solutions, that would be great. Obviously, you can do pass if you don't think there's any challenges or solutions. Same thing with the business model, and I will probably repeat this again. Last chance to the audience. Any questions or speakers' questions to other speakers? Starting with maybe Randy, if you see this CV2X and also CAV technology domain, do you see any challenges? And challenges are good enough, and if you have a potential solutions for research, you could actually share. Don't spend too much time, and you can obviously do pass. Start from Randy. Use the microphone.
With the automated vehicle, there's many sensors on there. So basically having the data fusion, so each sensor provides their data in a timely fashion and also the right data, because you can't overwhelm the cars and the system with unnecessary data. One thing at C2B2X, the standards was written in a way, short, precise information that should come from communications. So there's big complaints out there that, hey, it doesn't cover everything. We never intended that BDX communications to make a car into, let's say, a remote control car. That would be dangerous. So I think a lot of stuff is in place from a protocol functionality standpoint, there's just a few society issues as far as trust, security, and policy that needs to be refined for this, and we really need application standards now to be in place, because one of the problems we have is the slowness of applications, maybe the fact that different regions or cities have a slightly different twist. So it's hard to, so let's say, a standard to cover a certain application across the United States, because there might be a few states or regions doing it slightly different. And that's the same way in Korea. They can take everything that's the basic standards, that we can so-called allow so-called tuning for that region, so everybody gets the benefit of it.
Thank you. That was great. I have to remind that we have 20 minutes or less, so if you could actually make a key point about technology and challenges. Jun?
Okay, so I don't think you have enough time, so I'll make it quick. I think one of the main challenge from my context, because I'm also working as building global communities. So interactions to a human being and also like pedestrian bicyclists might be one of the major challenges eventually, because whenever we are crossing intersections and actually we are communicating with the drivers. So once the autonomous system came up, and then we have no means of actually making and also any kind of communications. So that's all the challenges. And so sometimes I was talking to also bicyclists. So this multi-lane case where they say the bicycle lane may be not a problem. A two-lane highway was a bicyclist who was actually on the two-lane lane. And how those vehicles following, probably, I don't know yet, based on my understanding, but because might just following the bicyclist, unless we are providing good algorithms to testing bicyclists. So that, anyhow, so that those will be one of the main challenges from my context.
So,
Thanks. So I think the main things will be successful stories and business models. So for success stories, like since CV and AV or CAV was proposed in 1990s, and these are like almost 30 years, and we really have limited deployment and success stories. You might want to ask why. And technology changed, and people questioned where are the CAVs outside there? You've seen any? So that's one thing. And also, like, there are some different understandings of the technologies. From one perspective, we don't have much connected vehicles like as infrastructure based. But on the other hand, for each automaker companies, their vehicles are pretty much connected actually right now with the cloud. So how do we really get to those vehicle automakers and like try to get into put their skin to the game and try to be interested in this game? Instead of cutting off connected vehicle departments, office, that's what they were doing in the past few years actually. How do we make them think that this is profitable would be a challenge?
thank you. Anders?
So from my perspective, I think one of the future challenges is within the communication of human-driven vehicles and connected automated vehicles. What I mean by that, if we have nowadays, if we drive a car, we can communicate as the drivers and with gestures.
Sorry, Andres, you have to turn on the mic. Thank you.
Okay. So now as the drivers can communicate with other drivers through gestures, right? If you are in the intersection, you can. But what if you are driving your car and interact with the autonomous car? So one way to address this is by integrating large language models into the human-driven cars and create the opportunity for human drivers to communicate and message autonomous cars in a sense that you can yield. We see in the video. I don't remember who showed this video with the autonomous car going all the way through the different directions in the intersection in Arizona, right? So in that particular case, the human drivers could communicate and provide directions or suggestions to the autonomous car. So I think that might be one way to, one challenge and at the same time some opportunities in this domain.
Thank you. Simeon, please turn on the microphone.
Yes, I have. I might combine actually two of your questions here, because I think the aspect human is going to be very important. I would concur that interactions are very important, but I think acceptance is also going to be a major issue. If humans are not confident with the systems, so they don't have a good understanding of the systems of their own vehicle or of any automated vehicle they're driving, then that's going to lead to dangerous situations. And I think also it's going to affect the goodwill that there is towards autonomous vehicles. So I think that's very important. I would also say that maybe we also have to address, well, I don't know if we're going to necessarily call it driver training, because if they're going to be users, they're going to be users, maybe user training, because certainly before we get to fully autonomous vehicles, the human, the user is still going to be active there, and they're going to play some sort of role. And if they don't have an understanding of the system, if they don't know when they have to use it, or if they, for example, don't know the capabilities of the system, then that could potentially lead to quite dangerous situations. And we already have numerous examples of situations where there's just been confusion from the user in the autonomous vehicle that has led to accidents. So I think that's maybe an important issue. Focus on the acceptance part, but also focus on the interaction with the user or the driver and also the autonomous vehicle.
Thank you. Ben?
Yeah, as I've been working for autonomous system to cooperative system, I would like to cover these challenges in different ways. So as I summarized in my presentation, the challenges remains technical challenges. We have the performance issue. Basic technology we're talking about is not only sensing, but also positioning, absolute positioning, relevant positioning, and also data processing, and then communication. So I think this week we're talking about mobility of the future and what technology can help or cannot help. If we choose cellular or something, what is the added value? Or if something we have already done. So the key question for researchers is not what it can. A lot of things you can. I can model many things. I can simulate many things. But for deployment, we do need reliability and robustness, and that's the key.
Thank you. Rahul?
So I have 2 points to make. So the first point is, no matter how much research we do in connected and autonomous vehicles, you have to understand, what is the business model? So for connected vehicles, who's going to pay for that, right? If company A says, oh, I'm not going to add $800 for my connectivity because company B has a different protocol, or they settle on the same protocol, but the users can't use it till there is 6, 8, 10% penetration, you just have this bootstrapping problem. Nobody pays for it. The infrastructure, these RSUs, in the US, the US government is not going to pay for it, right? They're not going to fund that. They're already broke. So I'm just saying there's no business model, right? So we have to understand that as researchers. We have to figure out where's the business model. For autonomous vehicles, if you're trying to run robo-taxis, who are you competing against? Uber? In the US, Uber is paying less than minimum wage almost now. And so you're competing with the rock bottom. Okay, you have a $400,000 car and you're competing with minimum wage person. Is that a good business model? Why are all the other companies dead except Waymo? Because Waymo has infinite pit of money over there, right? So 2 negative points. The positive point is, okay, well, what's the real, the main issue? Well, there is, the interaction with humans, the sensors, but at the end of it, it's all about trustworthiness in the overall system, not just trustworthy AI or trustworthy, it's a reliability aspect, but how do we prove trustworthiness? And that is an elusive concept because autonomous vehicles are in very complex scenarios. And I think breaking down trustworthiness is key to communicating that.
Thank you. Jason, do you want to add anything?
Well, people and human make a mistake as machine or technology do not make a mistake, but I think differently. It's because technology and or connection things, it's actually getting faster and faster, but it's still having, well, making mistakes or problems in connections like a latency or maybe packet delivery rate or something like this. So I think more important is not speed, and I think important thing is, do you have a backup process for that? So maybe what DSRC can be a backupper, or 5G network, or 5G can be a backupper, well, DSRC. So I think those kind of strategy and backup process is also important, and maybe more important in some cases.
There was a business model on this domain of autonomous vehicle called the shared autonomy. Instead of people owning cars and those, and you probably heard about it, that's a potential solution. Secretary Chow was in charge of a transportation department in the US. Her acceptance on this autonomous vehicle was, can I put my baby car seat in the car and then drive alone? And I wasn't ready, nobody was ready. It's going to take a time. So anyone can speak up about all three, or business model, or acceptance. Anyone just go ahead and then talk. You want to talk?
For me, it's not, if you talk about business case, first of which use case. A lot of use cases make no sense at all. I can tell you from ITS domain. This is really just some bizarre, always make a long list of use cases that has no business case. That's why a lot of things didn't happen.
Another take to that. So I think, the seatbelt, for example, if you leave it to the companies, they will never implement it. Regulation has to come in. And there was a big regulatory movement in the 60s in the US, and the companies fought back. They fought back very hard. It went to the Supreme Court. The car seat laws, the airbag laws, all of that is, so you can think of it as, companies will decide. They will not decide on, safety features that are required. That comes from the regulatory side. So say from the DOT center that we operate, we are building the technology, but we are also building the policy. And we have a lot of engagement with senators, with the Congress people, explaining to them what is the technology, how does it work, and so on, right? So I think that's one part. The other part is also to say, how do we show, like as Meng said, where are the success cases like that, right? So the success cases are in logistics, in cargo, in agriculture, in mining, in these closed systems. Autonomy works very well there, and that's where it has to start and grow.
Thank you. Meng, do you want to say a few words? Oh, and then Shaw.
I really appreciate this question. I think that's exactly why we're here. We want to talk about. So mobility, well, first need to clarify, ITS traditionally is automotive industry, not Tesla, not Waymo. Those are not, by my definition. So first is safety. And safety, where does the business model come from? So robotics was doing robot already in 1980s. No business model. So you can play football. So what would be the useful use case? So they think about use for the car. That's a good use case. But they don't have industry support. So there's no business. So ITS sector started with automotive driven. This is a new selling point. That's why we had ADAS. We still have ADAS. Actually, automated driving is just ADAS, more robust to a higher level. The goal is not to remove the driver from the car. The goal is to make driving safer. Not only driver inside the car, also people outside the car. And then we also extend it to the whole traffic management, to the efficiency, to the fuel efficiency, and then sustainability. And then come to the concept. So what is mobility for? So in the past, engineers will talk about efficiency. And then now we have this umbrella, sustainability. And in the future, we expect to talk about the quality of life. But what is the definition? We have all the different definitions. That make things more complicated. So to answer this question, actually struggled for us is that what is the really selling point? And if this selling point is driven by the industry and the policy support, because decision makers, nobody can say safety is not important. That's why we had funding we had the industry, private investment, we have the business. And now we are struggling. So it's not just we have communication, we have a more robust system or not. So they're all related. Also, what is it for? What is life for?
Thank you, Shao.
I want to bridge Andrew's and Rahul's information a little bit. So I think the first driving force would be market, but regulation policy is also necessary.
You need to turn on mic. It's a technology issue we have.
All right, sure. So here we get connected. Yeah, sure. So if you look at the history, you know, like Ben said, ADAS technology starting from early 2000, there is almost no ADAS technology. But right now, yeah, ADAS or ADAS, you know, but right now you see the market has already received it, and no matter how safe they are, actually, you know, they have been sold out to lots of the vehicles, and so. But the other ways, like we set up an architecture like us, you know, I was imagining like connect automated systems. Suppose that's actually, if the governments want to start too much of these technology architectures without understanding that the industry and these players' incentives and limitations and preferences, maybe lots of times these big architectures may not work. Like we have observed lots of ups and downs over the history. Like 1960s, there is a motion of putting like cables under the pavement to make it automated, you know, huge money put to it, and it didn't work. And 1990s, I think also U.S. Government put lots of money and it didn't work. I mean, maybe part of that is government is not big enough to support it. Part of that is we probably want to make the government moving towards the industry. Having said that, I mean, governments probably is still necessary, you know, like insurances, like some of those safety testing standards. Let's say I talked to the state DOT folks, and he said, if a company talks to us, okay, I have a technology, autonomous vehicle, can you allow us to test in your state? How do we answer that kind of things? Right.
Thank you. I want to ask
Can
one.
I very briefly talk?
Oh, sure, yeah.
Yeah, I think a very simple logic. The money talks. So where there's money, it moves. I mean, it was actually the history already showing that everything was driven by actually market and business and the money. I mean, same thing. Autonomous vehicle, if there are money available, people are coming and then buy, or maybe selling the companies, so that.
History has shown that safety can sell in the transportation world, and with the federal highways could act some part in the so-called the safety rating of cars moving forward, and we may apply communications there. We've seen what happens when we went from the mobile phone to the smartphone and the power of communications. So hopefully we can see that in the vehicle and we can apply it appropriately, like in truck platooning and emergency vehicles and that stuff. Let's see how that plays out instead of trying to tackle the whole thing for all cars per se.
Thank you. I wanted to ask, do you guys want more discussion, or you had enough, so this is it? Anyone want to have more discussions?
I have one question for your answers, because just one comment for that. So my thinking is like this: thinking about the urban design, most of urban design emphasize on the transit-oriented development. So thinking about public transport and any other alternatives of transport, how can combine this autonomous vehicle in the future? That is my question. But there is no need to answer for that. Yeah,
I bet we can talk hours and hours. That's why I asked you. Right.
Next time.
Since I am in charge, I want to make just a few quick comments. One is history is important for us to learn, and most of innovation is coming from, not from government, but from industry. Somehow this autonomous vehicle started from government. If you all remember DARPA Urban Challenge, no one knew this would happen, but it worked, but industry took the leadership. Chris Omsen actually got a position at the Google and started this thing and made an impact. So industry seems to doing better things, even though it started from government. That's one point I want to make. Closing remarks supposed to be done by Jason, so you can actually close.
Okay, well, thank you for the great discussions and the questions from the audience. Yes, we have, well, it seems we have so many questions, and that's a good sign for our topic. Our topic was, it's interesting, so that was the proof. So thank you for the paying attention our today's event. If you have a question, you still have plenty of opportunities because we have a program tomorrow, the day after tomorrow, even Friday. So if you can make your trip to Songdo, which is a great place, then there will be a chance. So please stay tuned and look for, so let's look for the main events from Wednesday to Friday. So thank you very much for our great scholars, audience, and the guest speakers, and our organizers. So thank you very much. So thank you. Yeah.